don't. Okay, just double check.
Rusty,
I'm
we've
fine.
got 20 minutes. You're going to talk for 15.
Sure.
I'll wave
Very
you
good.
at- I'll
Yeah.
wave you at 10.
All right.
Perhaps
Thank you.
we could give a 5 minute.
How am I advancing the slides? Like that. All right. Thank you. So you've got the title. I'll just give you a quick point it. Do I point it somewhere? Okay. This is just about my lab and sponsors. I'm basically a combustion engineer, but I'm going to talk about not burning stuff, and I'll explain why. Because my whole background has been in engines and combustion, and all these companies that have funded my work are all combustion related in some way, NASA and other places. But the problem that I've been working on, just to explain the motivation, is that combustion is 80% of all energy use. It includes, the rest 20% include nuclear, wind, hydro, everything else. There's two ways pretty much all combustion processes work. One is sort of a constant pressure free expansion mode, like just an open fire kind of thing. What happens then is that the hot gas is free to expand and pushes the surrounding gas, and that's energy wasted. Basically, you're just pushing the atmosphere aside in this picture. Whereas in a piston engine, you put the fuel in air and you confine it and you generate pressure that pushes on the piston, does work. You can get work out of both processes, but you get more work out of a confined, constant volume combustion process. And that's a typical piston engine versus the upper one is your gas turbine engine that has a constant pressure process primarily. What we would like to do is replace that constant pressure process with a constant volume process, even in a gas turbine in other situations where you want continuous flow. The challenge is this is necessarily a cyclic process. You fill a container, you burn, you discharge, but then you want to embed that in a continuous flow process, and that's the challenge we've been working on. And I won't go through all the thermodynamics, but it's very easy to show. Okay, sorry. It's very easy to show that thermodynamically, the constant volume process, if you could replace the constant pressure process, the constant volume process would be better. And the way we do it is basically by having a large number of combustors on a drum that rotates. And the best way to look at what's happening inside is kind of open it out, and kind of use what's called a developed view. So any one of the combustion chambers will discharge any gas it has, will be filled with fuel and air as it moves vertically upwards, which is equivalent to rotation. And then when it's filled with fuel and air, we ignite it by just basically transferring hot gas from one chamber to another. Burns very fast. We want it to burn very fast, and then you get the high pressure at the end of the combustion process, just like in a piston engine, except this is much more compact and much lighter weight and can be easily fit into an aircraft engine. And that's why Rolls-Royce and NASA and so on have been interested in this. And this project continues. And let's see if this works. I don't know, but it's just a short video of the engine actually operating, the combustor actually operating. Yeah, I'm not sure that's gonna work. I'm gonna skip that. So it just makes some sound, and you see some, it's a short duration test that we did. We've done a longer duration tests now on a separate high pressure version of this. And so this is ongoing research. But the reason that I'm particularly interested in changing the fuel is because this works perfectly with low carbon, high hydrogen fuels. Not necessarily pure hydrogen. You don't need that like in a fuel cell, you need pure hydrogen. But here, just a high hydrogen content accelerates the combustion process and works very nicely with this. Not that it won't work with methane, it will, but it just becomes a little bit larger because you've got to give extra time for combustion. And so we're doing a lot of research on the ignition process with different fuels. So what I want to advocate is just basically stop burning carbon and try to get the hydrogen part and just burn that. Okay, so why? Carbon is such a fantastic element, right? It's got, I'm sorry, I'm not speaking into the mic as I should. I try to remember that. So carbon, as you know, is the basis of life along with water, and it's got, all these immense number of compounds that it forms, and organic compounds, and then the ones that are the basis of life are, again, just millions of compounds. And all of them have high value in some way. For life, obviously, have high value, but we can have high value compounds of different kinds. Just as an example, in recent years and decades, there's a lot of research going on into nanoscale carbon nanotubes, fullerenes, and so on, all these different structures that you can create at nanoscale. Perfect carbon nanotubes are the strongest and stiffest materials really known, that as far as I know, that have been measured, but at nanoscale. If you look at, for example, the tensile specific strength on a per unit mass basis is 1,000 times that of low carbon steel for multi-walled carbon nanotubes. Theoretically, it could be even higher from some predictions. Of course, larger scale structures that you can make with carbon nanotubes, the actual strength and stiffness will depend on the microstructure that you get in the process of forming those larger scale structures. Another interesting thing about carbon as an element, not all the different compounds, but pure carbon in its elemental form, there are many different elemental forms, all the way from what you find in coal to what you find in diamond, and a lot of things in between, like including carbon fiber, carbon black, and so on. The cost, varies immensely as well. For $10, you can get a megagram or a ton of coal or 1 milligram of diamond. What's of really interest to us is carbon fiber is about 1 kilogram for $10. So I think, what a conference like this, really, should be looking at all of the big scale things that you can do. And if we can lock up carbon and not burn it, not make CO2 and then try to store that, which is very difficult, even to extract it and to store it is in my opinion, has not really worked. I mean, in the US, we had a major project by DOE, the Kemper County project. It really didn't work out. It was too expensive. And there's really nothing going on in the US, as far as I know currently, that's really looking at it on a big scale. So the other thing about CO2 is it has, like water, it has no useful energy content, right? So, there's discussions about taking CO2 and doing something useful with it, but if it doesn't happen at the same scale as you're generating carbon dioxide these days, it doesn't make any sense. You can make, some drug or something, but the scale is really too small to make a difference. Plus, the energy you're going to use is going to be more than the energy that you get by burning carbon, so why just not use that energy directly and not go through that cycle in the first place? So the question I want to answer is, can we make carbon more valuable as a material rather than as a fuel, and then have hydrogen-rich fuels that you can use? And I think really the place that you can do that is in structural uses where you use it in large scale, not small scale, but aircraft already do that, but can you do that for buildings? Can you do that for many other large-scale uses? At Purdue University, we have some work in the direction, not exactly what I'm going to be talking about. There's an ERC that's looking at taking gaseous fuels that we have in abundance in the US now and converting it to different kinds of chemicals, including liquid fuels. I don't like the liquid fuels part as much because you're going to burn that again. So, but other high-value products are also being looked at. So going back to that list of different elemental forms of carbon, the volume of use is important to look at. Right now, carbon fiber is a small amount compared to the amount of coal we burn. But if you look at the amount of steel that we use, that's of the order of magnitude of carbon. Okay, so I've got I've got a lot of material here about carbon fiber and the benefits of it, and some of the description of what actually it looks like at the small scale. But the key is that it has all these wonderful properties that make it very attractive, but it's expensive. It's still being used for aircraft. Half the weight of essentially an older generation airplanes now being replaced by carbon fiber, some fully carbon fiber aircraft as well, wind turbines, use a lot of it, high-end cars, but we want to bring it to low-end cars to really make it high volume. I'm going to skip some of these slides. DOE has done lots of studies on showing the specific strength and specific modulus of carbon fiber itself. There's folks looking at carbon nanotube reinforced composites. But the real issue is the precursors that are being used currently are very expensive. Polyacrylonitrile is what's currently used. There's a long series of steps to make it, which make it quite expensive. And it's still the best in terms of strength. There are other things that have been looked at, but it's still the one that has the highest strength. And if you're going to use something else, we need to look at various properties, particularly anisotropy of the polymer that's used. Oak Ridge National Lab and Japan are some of the, Kyushu University in Japan are some of the places where this research is being done. One approach that seems to make sense is to use polyethylene as the precursor. It's cheap, it's widely available, can be made from shale gas and other fossil gases that are available depending on what the feedstock is. There's different processes from ethane and from methane. But the challenge is that it's not as strong what's made currently because it's a thermoplastic material. But there's processes, specifically sulfonation, that allows you to form crosslinks and make it stronger. And that's there's research going on that, and that seems to be a very good way forward to use polyethylene. You can make some really interesting, neat structures with it. And there's a lot of research going on to continue to improve the properties of polyethylene-based material. There's work on carbon nanotubes also being woven into larger scale structures to make carbon fiber and sheets. That's also something going on. There's work on biomass to carbon fiber. There's old work on coal. I don't think there's anybody really doing that. Just in the last couple of years, there have been a number of projects funded by ARPA-E and DOE into separating carbon into useful materials. And so my conclusion is that this is something we want to encourage, this trend of really using carbon as a material and not burning it, and creating high hydrogen fuels that you can then use as fuels for burning. So I'll stop there and see if you have questions.
So remember to state your name, question, thanks.
Rob Sapien from NREL. Question, I want to go back on the fuel side. So you're saying you use a high hydrogen fuels. Are the materials there for us to burn more hydrogen-rich fuels for gas turbines and IC engines? It's because it burns much hotter. Are our materials there for us to start using that?
Yes. The temperature actually isn't that much. It's a little higher. It's not that much that So there's been a lot of internal combustion engines, gas turbine engines that have run on hydrogen. There are issues with respect to the fact that hydrogen burns a lot faster, it fuses a lot faster. So controlling, especially a pre-mixed hydrogen-air mixture from flashback and issues like that have to be resolved. Combustion oscillations, when you have very fast-burning fuel like hydrogen, have to be addressed in gas turbines. The work I'm working on, the wave rotor combustor, the pressure gain combustor, actually takes advantage of that and does not suffer from flashback and combustion oscillation issues. So that's a special reason that I'm interested in high hydrogen docking fuels.
Hi, Robert from Harvard. So I have a question with high hydrogen. Do you have a problem with propulsion then? Because if you're replacing some of the carbon for hydrogen, do you have to pay a penalty by having more mass go through? I'm thinking MV propulsion, and then you have for energy 1/2 MV squared. You're going to lose on your mass.
Well, I'm talking strictly about air breathing propulsion now. Actually, for rocket propulsion, hydrogen is great too. But essentially, the mass is essentially air. Nitrogen is the main mass. It's how much energy you add to it by burning fuel. The mass of the fuel really doesn't play in that very much.
I just had one more question. It's okay. Are you also looking at imidization or cross-linking with other materials to increase your properties and yeah?
So, the polyethylene fibers, polymer can have higher strength carbon fiber if you have the cross-linking to a certain extent. You still want to have the anisotropy of the material. But whether you can cross-link with other materials, I have not looked at that. I know that if you put carbon nanotubes in other polymers, it tends to make them straighten out, have more anisotropy, which helps with the properties of composite materials, carbon nanotube embedded in other polymers to make composite materials. So I'm not sure I answered your question. But
Yeah,
that's
thank
what I
you.
know.
Any other questions? I have a quick question. So, so effectively so you're talking about taking the petroleum products and converting them, before they're combusted for something else, correct?
Right.
But so my question then is, I mean, having worked in the oil sector for so long, is they'll say, great, we have another market, so we're just going to produce more. So I'm just wondering are you planning to make or is it just assuming a
I'm fine
decarbonization?
with the oil and gas industry making money on high value products that don't damage the environment.
So you're
Right.
just saying, well, that's great. So presuming that there's some carbon price or disincentive, you're just going to say, here's this other alternative.
Well, I'm not even assuming, it would be great if there is carbon pricing and an environment damage tax is what I would call it. But if carbon as a material, such a fantastic material, has high value, then that by itself will incentivize them to separate the carbon and the hydrogen and sell them for two different purposes. Hydrogen for burning, so there's no CO2 into the atmosphere, the carbon for other high value products. You're going to lose half the energy roughly. Right? So high carbon, half the energy comes from hydrogen, half the energy comes from carbon, roughly speaking. So that means your fuel, your hydrogen is going to cost twice as much essentially for the same amount of energy. But you can offset that with the revenue from high value carbon products. And I hope that'll work. But that's the proposition.
We all hope that all of our solutions are going to work. Any last
All right.
question for the speakers? This one last one here. I think we have time for one
Yeah,
more.
we're fine. Good.
Thank you. My name is Xiao Yuan from MIT. So my question is, so you have these hydrocarbons, you want to convert them into carbon materials. So how can you increase the selectivity of a certain type of carbon, for example, instead of just coke? Yeah, thank you.
So that's really the challenge. And chemists and chemical engineers are working on that. There's so many different forms of elemental carbon. So one project that I mentioned is just DOE funded, where you take methane and bubble it through liquid metal, and you break the bonds, and the hydrogen bubbles up, you get hydrogen, and then you get a layer of carbon floating on the top. But that's currently the way they're doing it is sort of more or less like carbon black. It's not, it doesn't form the high strength structures of carbon nanotubes or carbon fibers. So there's a lot of work to be done. Yes.
Okay, let's thank our speaker and we'll move on to the next.
Thank you.
Okay, so we are on our last speaker for this session. We have Ian Scott from